Hello PreCalc again. We're back at part 2, and I want to just make sure before we actually do our next example or first example that you truly understand the difference between linear and angular velocity. So how could you go on in life without it? So let's look at this statement. If you would jot it down, you may always turn the video to pause while you're doing that. All moving objects have linear velocity, whether they're going in a circle or they're just trekking on down a straight path. They all have a linear velocity. Objects in circular motion, however, have both. They have linear velocity and they have angular velocity. So, continuing, we use this symbol, that's the Greek omega. The lowercase omega. Omega is, I may refer to it as W, but omega is the symbol for this angular, remember the angle is changing, the angular velocity. Typical units would be radians per second or revolutions per second. Do you see how this part, radian and revolutions, capture the idea of circular motion? That will help you if you do. Velocity in linear direction are velocities that we're used to seeing, like meters per second, centimeters per second, feet per second, minutes per hour, miles per hour. So these are typical linear velocities, always a distance divided by a time. Here I have a string, and I've hung connected three objects to the string. I'm going to spin it, and as I do that, I was wondering, what is the angular velocity of object 1 as compared to 2 and compared to 3? Well, object 1 is going to go around in one entire circle. How many radians is that? Remember, we learned that halfway around the circle was pi radians, and then all the way around the circle is 2 pi radians. So the number of radians per second, let's say it takes 1 second to revolve this around. So we'll say we have 2 pi radians for object number 1. Object number 1 is going to go around. I'll trace object number 1, object number 2, and object number 3. So, they're all connected to this string, but this dotted line will trace the path of each. And object number 1 goes around 2 pi radians in 1 second. So I have 2 pi radians per second. 2 pi radians per second, per 1 second. What about object number 2? As it goes around, can you see that object number 2 with angular velocity, it goes around 2 pi radians as well. It goes one circle in 1 second, and so does object number 3, 2 pi radians per second. Another way we can say that is 1 revolution per second. So in this case, this is also equal to 1 revolution per second, so is this, and so is this. Since they're all connected to the same rope, and the rope is spinning at the same angular speed, they all have the same angular speed. So let's look at what happens let's look in a different way. Let's look at the value of the linear velocity for object number 1, or at least just discuss it. I'll save the calculations for an example. But look at object number 1. Suppose you were sitting and riding on object number 1. You're going to go around this far in 1 second. So let's see if we have any colors. I think the colors show too much in the video, but give it an old try. So there's red, if you can see. I think I have maybe there's a green here. And the number 2 goes around in the green, and I guess yellow for number 3. Alright, so looking at the red path, this is red, pinkish red, the object is going to go this much distance in 1 second. However, object number 2 is going to go this distance in 1 second, and object number 3 is going to go this distance in 1 second. So which object is going the fastest? You're riding on 1, you're riding on 2, you're riding on 3. Because the distance gets larger as the radius increases, we see that they're all covering the distance assigned to them in 1 second. So this one is going the slowest. Number 1, he has the least distance to cover. Object number 2 has to keep up, so to speak, with the same time to get all the way around in 1 second. So he will have to move faster. And object 3, faster still. Alright, so angular velocity turned out to be the same for the 3, but it became increasing as from object 1, 2, and 3 in the linear velocity. Alright, hopefully that idea makes sense to you, and we'll see if it does when we finish this. As we finish this, we'll do some examples. Alright, the example that I want to do first, I suppose, is, let's do this one. Say there's a clock, and the clock has a second hand, as some clocks do. And this clock, the second hand, I'll draw it at this position, the second hand has a length, and that length is 10.2 centimeters long. And I'm going to look at the point of this second hand, the very tip where it's actually on the circumference of the circle, and I want to find the velocity linearly and the velocity with angular speed. So let's begin down that path. Because we're in centimeters, and because I know that the second hand goes around 1 revolution, or 1 whole time around the circle in 60 seconds. That's how the minute hand works. I'm sorry, the second hand works. So I'm going to use the unit centimeters per second, and that's one of the kinds that we have listed for linear velocity. So notice at the end I want centimeters per second. And in fact, that unit right there sort of guides the path in which I'm going to travel down this problem. So velocity, we learned in our 3rd or 5th grade class, is distance divided by time. And as we do that, as we look at that, what is the distance that